You know, we measure things all day, every day, from the ingredients for dinner to the distance we drive. But have you ever really stopped to think about the invisible rules that make all those measurements work? Turns out there's a hidden language that keeps our numbers honest and accurate, a language that everyone, everywhere can understand. And today, we're going to decode it. So, to really get why these rules are such a huge deal, let's just jump to the most extreme example you can possibly imagine. Up on the International Space Station, there's an atomic clock. It's not ticking, it's using the vibrations of cesium atoms to keep time. And this thing is so ridiculously precise, it wouldn't lose a single second for millions of years.
So what's the deal? Why this obsession with getting numbers so perfect? Well, it's about more than just making sure our GPS works, which is obviously important. It's about building a common, totally trustworthy language that lets us understand the universe itself. And to do that, we all need to be reading from the exact same page.
Think of a standardized system of measurement as a universal translator. It works for science, for industry, for, well, everything. If you want to collaborate on building, say, a skyscraper or launching a rocket, you absolutely have to agree on what a meter is or what a kilogram is. Without that common ground, you just get chaos.
What you're looking at here, this is basically the entire alphabet for that universal language. It's called the SI system. These 7 fundamental units are the building blocks for every other measurement we could possibly dream up. Things like speed, energy, pressure, it all comes back to some combination of these 7. Now, you probably know that while most of the world uses the SI system, the US often uses its own customary units like feet and pounds. And for mass, they sometimes use the slug. And yes, that's a real unit. But here's the kicker. To make sure we can all still talk to each other, every single one of those customary units is now officially defined by its exact SI equivalent. So, in the end, we're all speaking the same language, even if we use different words.
Okay, so living in a world with a couple of different measurement systems means we've got to get good at translating between them. But please, don't think of this as some scary math problem. It's way easier than that. Seriously. Think of it more like looking up a word in a dictionary and swapping it for its perfect equivalent in another language.
This here is a simple, totally foolproof 4-step recipe for any unit conversion. But the real magic, the part that makes it all work, is that last step. We're going to treat the units themselves, words like meters or feet, just like variables in algebra that we can cancel out. Let's see it in action.
All right, let's try a really simple one. We want to convert 12 inches into centimeters. Our dictionary for this little translation is the fact right there on the screen. 1 inch is exactly 2.54 centimeters.
So we take our 12 inches and we multiply it by a fraction. And here's the beautiful part. We set up that fraction so that the unit we want to get rid of, inches, is on the bottom. Why? Because that lets the inches on the top cancel out the inches on the bottom, leaving us with only the unit we wanted in the first place, centimeters.
And there's our answer, 30.5 centimeters. By just treating the units like algebra, you can be 100% sure you set up the problem correctly. This little trick is so powerful, and it works for converting anything, no matter how complicated it gets.
But you know, just getting the right number is only half the battle. The next step is all about being honest. Honest about how certain we really are. See, every single measurement we ever make has a little bit of uncertainty built right in. And that's not a mistake. It's just a fundamental, unavoidable part of trying to measure the real world.
This is the perfect way to picture it. Imagine you're using a regular ruler. You can see your object is a little past 1.4 centimeters, but it doesn't quite reach 1.5. So you take your best guess. You estimate that last digit. Maybe you call it a 3. Now that 3, that little guess, is actually one of the most important parts of the number. It's what we call significant, because it tells anyone who reads it that the true value is probably closer to 1.43 than it is to 1.40 or 1.50.
We call these meaningful digits significant figures, or sig figs for short. They're basically the digits in your number that you can actually trust, the ones you can confidently stand behind. They're the language we use to tell the world how precise our tools are and how much confidence we have in our answer.
So how do you count them? Well, any digit that isn't a 0 is always significant. Easy enough. It's the zeros that try to trick you. Zeros at the beginning, like in that first example, are just placeholders. They're never significant. Zeros trapped between other numbers, they always count. And the zeros at the end? They only count if there's a decimal point anywhere in the number. That's why 4.0500 has 5 sig figs and 50.0 has 3.
Okay, so let's put this all together. It's one thing to know what significant figures are, But using them when you start doing calculations, that's where the rubber really meets the road. And you can't just blindly trust what your calculator spits out. Your calculator is powerful, but it's dumb. It doesn't know how precise your original measurements were. But you do.
All right, rule number 1 is for when you're multiplying or dividing, and it's actually pretty simple. Your final answer can never, ever be more precise than your weakest link, which is your least precise measurement. So you just find the number in your calculation with the fewest significant figures, and that's how many your final answer gets.
Let's use this in an example. We measure a plate. The length is 8.71 centimeters, that's 3 significant figures. But the width is only 3.2 centimeters, that's only 2. The calculator gives us this long number, 27.872. But our weakest link, the 3.2, only had 2 sig figs, so our answer can only have 2. We have to be honest and round it to 28 square centimeters.
Now, switch gears for a second, because for addition and subtraction, the rule is completely different. This is a super important point. We stop counting the total number of sig figs. Instead, we look at the decimal places. Your answer can only be as precise as the measurement with the fewest decimal places.
Let's go back to that same plate and find its perimeter. We add up the sides, and the calculator tells us 23.82. But wait, look closely. The 8.71 measurement is precise all the way to the hundredths place, but the 3.2 is only good to the tenths place. That's our new weakest link. So we have to round our answer to the tenths place, which gives us 23.8 centimeters. And check this out, our final answer has 3 significant figures, even though one of our inputs only had 2. See? For adding and subtracting, it's all about the decimal place.
So, what's the big takeaway here? What does this all mean in the real world? Well, these rules are the difference between just guessing and actually knowing. And when the stakes are high, getting it wrong can be, well, catastrophic. In 1999, NASA lost its Mars Climate Orbiter because one engineering team was using metric units and the other was using imperial. That simple translation error cost a spacecraft. These rules really, really matter.
So really, what we've done today is put together a basic measurement toolkit. We have a universal language in the SI units, we have a foolproof method for translation with unit conversion, and we have the rules for honesty, significant figures, that make sure our results are grounded in reality. This quote really gets to the heart of it all. Measurement isn't about finding some single, perfect, absolute truth. It's about being honest, having integrity, and admitting that our knowledge has limits, and that last digit is always our best, most informed estimate.
And that brings us right back to where we started. From that last estimated digit on your high school ruler, all the way to the mind-boggling stability of that atomic clock on the space station, the exact same principles apply. This isn't just a bunch of boring rules for a science class, it's the very foundation of how we build a reliable, shared understanding of our world.
So I'll leave you with this question. Now that you speak this hidden language, where do you see the need for it? Is it in the nutrition label on your food? Is it in a contractor's estimate to fix your house? A medical report? Where do honest numbers matter the most to you?